If we exist in an ocean of matter, then we should be able to make waves in this matter, in this stuff. If we're all just fishes in a large ocean of matter, then we should be able to make waves in it. And we do. We do it through electromagnetic waves, but also through sound waves and audio waves, you know. But we're more interested here in the electromagnetic waves. Now, here's a wire, and the only way to make electromagnetic waves is to move electrons, like, through the wire. Like, you move the electrons up the wire, and you move electrons down the wire, up the wire and down the wire. And when you're doing that, you're making waves. And those waves can be received by another wire quite some distance away. And so if electrons are moving up and down in this wire, then far away over here in this wire, you know, very far away, it'll catch the wave and it'll push the electrons up and down in this wire. So what we do for electronic communication these days is, whether it's cell phones or radio or television waves or satellite microwaves, we always move electrons through a wire. Electrons move like this, and then they're received by another receiver far, great distances away, and the electrons move up and down in the wire like that. Now, of course, you can make the antenna go this way, electrons can go back and forth this way. You can hold it this way, electrons can go back and forth this way. Or you can even have the wire be in a circle and have the electrons go like this, and this, and this, and this, back and forth, and that back and forth action produces waves. And that's exactly what a transmitter does. A transmitter pumps the waves, pumps the electrons up into the wire and pulls the electrons back in, and pumps the electrons up and pulls them back down. And that's what a transmitter does. But what a receiver does, some distance away, is when it receives the waves, the electrons get pushed down and pushed up, pushed down and pushed up, and that goes into a wire that goes into the receiver, and that pumping action is received by the receiver. This video is about waves, magnetism, and diamagnetism. Now, you can't make a wave without pushing on or pulling on a medium. Now, when you're listening to my voice right now, what happens is I'm pushing on air. I'm pushing and pulling on air. And the same thing happens with this ocean of matter that we're all in, the stuff that's much, much finer than air, much, much smaller than air molecules, this stuff that's very, very fine. It's just stuff like anything else. Electrons are stuff, protons are stuff, and the stuff smaller than protons and electrons, it's just some more stuff that's in smaller pieces. Now, this stuff is out there in the universe, way, way out there, even in what we thought was the emptiness of space, where it turns out space is not empty. We can see the light of the sun only because the waves from the sun can travel through the medium and reach us. Now, this is inevitable and is the principle of all waves, because you have to have a medium in order to push on that medium, in order to pull on that medium. You have to have something to push on or to pull on. And that's the essence of any wave. So when in a wire you have electrons shooting up the wire and shooting down and shooting up and shooting down, what's happening is those electrons are pushing on the ocean of matter that we're all in as they travel through, just like a motorboat through the water. Only instead of being on the surface of the water like a motorboat, the electrons are underneath the water, just like we all are. But still, the same waking action happens. Say this is an electron and say it's moving through the water. When it moves through the water like this, it's going to leave a wake behind it in the shape of like a cone that comes right off of the electron as it travels through. And this is what's responsible for magnetism, as we're about to see. But first, let's see what a motorboat would look like on the surface of the water. Here we have a shallow pan of water. And in this shallow pan of water, here we have a little Lego motorboat. Now this little Lego motorboat's going to race through the water. See if you can see the V that forms at the head and behind the motorboat. Did you see the V that streamed off both the head and the tail of the motorboat? The same thing can happen when I use my finger. You see that the water piles up in front of the finger, and the water dips down behind the finger. What's happening is there's a high pressure area in front of my finger, where the water piles up, and that streams off to the sides of my finger, and so that wake becomes a traveling wave. Behind my finger, there's also a traveling wave, and what happens is it's a low pressure area where there's less water behind my finger. And that low pressure area streams off the tail, the back end of my finger, in a V as well. Here you get a better angle of the low pressure behind my finger and the high pressure that forms in front of my finger. Do you see the water pile up in front of the finger and stream off like a wave, as well as the low pressure, that is the dip behind my finger, that streams off the back end of the finger? But what does a trailing wake off of the head of an electron and the tail of an electron have anything to do with magnetism? Well, the answer might surprise you. So here we have, say, an electron, and here's the high pressure part that builds up in front of the electron, and it streams off the back like this. And off the back of the electron, here we have a long, drawn-out, low-pressure part where the electron left. And it's much, much longer. So here we have the high-pressure part of the wave, whereas back here, we have the low pressure part of the wave. And you can see in these various areas here, the low pressure part of the wave that trails behind the motorboat or the electron in a cone shape because it's underwater, the electron, this is a very long distance compared to this shorter distance. So if we take a section of this, say this section here, we can see a very short high pressure area that's strong and short, and a low pressure area which is long and weak. So we know that these two are equal and opposite to each other because what the high pressure area lacks in length, it makes up for in strength. But what the low pressure area lacks in strength, it makes up for in length. But why would these two pressure zones, different lengths and different length and different strength pressure zones, have anything to do with magnetism? Well, because it affects matter differently depending on if the matter is stuck or not. You see, if you have an electron, as say this wave that's coming in, just looking at this very small section here, say here's the high pressure zone, and here's the longer drawn out low pressure zone. And when it hits an electron, now it's traveling this way. When it hits an electron here, there's your electron. When it hits this electron, because it's moving this way, this high pressure part of it hits the electron like a hammer hitting a nail. And if this electron is stuck, it will bounce it, it'll push it out and pop it out of the hole it's in. But if the electron is not stuck, and the same sort of thing happens, where here you have the incoming wave, we're just looking at a small section of the wave, and you have the high pressure zone and the low pressure zone that's behind it, and it hits the electron that's not stuck but is very loose. Sure, it will bounce the electron forward, but what will happen is if the electron is not stuck and it's loose, it will be better accelerated by a long drawn out zone here, the low pressure zone. So when this electron that's loose, so this is a loose one, loose is better accelerated by the longer zone here. And stuck in a hole is better accelerated by the high pressure part. And it's thrown this way, whereas a loose one is accelerated that way. So it all depends on the situation that the electron finds itself in. In iron, we have electrons that are stuck in a hole. 1 electron per atom in iron is able to take part in the magnetic process. And this electron that's stuck in the hole is able, once it's unstuck from its hole, it's able to whip around the nucleus when it's hit by the wave. It does so above all the other electrons towards inside the nucleus. Say this is the nucleus and the inner electrons. And then here's the electron that's able to go around the nucleus and the other inner electrons. So once it's hit by the wave, it can whip around its atom like this. But iron has 2 outer electrons, not just 1. And that's crucial to understand because the other electron is helping to form a shell above the nucleus. So you have this electron, and imagine another electron above it, or wherever, helping to form a shell around this atom. And how that happens is very interesting. I have here a rock book which shows the crystal structure of iron and nickel. Both, this is very strongly magnetic. And if you can see it there, nickel iron says strongly magnetic there, and the crystal shape, as you can see right there, is an octahedron. And that's important to understand, that it forms an octahedron, because that's what the other outer electron that's not being used in the magnetic process is doing for the other electron, the other valence electron. So just remember that octahedron shape there. In an octahedron shape, what's important to realize is that it only takes one valence electron, that is one outer electron, to form it. So here we have an octahedron. And beside it, we have another octahedron. And each one of these is one atom of iron. Now you can see the shape here, and here's, if we're looking at just this atom here, we can see one electron in front, one behind, one at the top, one at the bottom, one on the right, and one on the left. Now, if the electron we say that's bonding between these atoms is the one that's up here at this corner, then the electron here that's shared between atoms belongs from this atom here, and this electron is covering that one. The one at the bottom here would be this one from the atom down here. This one here is from this atom, and this one is from the atom that's in front that you don't see, and the one that's here is from the atom behind that you don't see. So we see that this bonding arrangement, it only takes one electron per atom to make this bonding arrangement. To prove this further, let's take a look at gold. There's Au, or gold. And gold, as you can see, also forms an octahedron shape, as you can see here. And it only has one electron in its most outer shell. So what does this mean for iron, which can form an octahedron-shaped bonding pattern with its atoms, thus only using one outer electron instead of two? It means that it's able to create a shell around encasing the other electron. So this circle inside represents the nucleus and all of the electrons around the nucleus, which are, with the matter around them all dense. Obviously this is a two-dimensional drawing of a three-dimensional happening anyway. So here's this electron, which is helping bond between atoms, and here is the other electron underneath it, able to free and able to roll around inside the shell. Free to an extent. It's a little stuck in a hole, just a bit stuck, and that's why, because it's stuck in the hole right here, that's why it needs a strong wave to pound it out like a hammer hitting a nail. And when that happens, it will whip around its nucleus and all the other inner electrons inside this shell that's created by this other electron. And that's why, scientists have not realized for a long time, but that's why you need two electrons in order for iron to take part in the magnetic process. One to form the shell, and the other one to actually do the moving around the nucleus when it's struck by the wave. Because it's in the hole, it needs to be struck by a hammer-like wave. So when that short high-pressure part of the wave comes in, and followed by the long drawn-out low-pressure part, this intense high-pressure part, when it smacks this electron here, that electron's going to whip around the nucleus like this. What's going to happen with this long, drawn-out low pressure? Because you see, when this high-pressure part hits this electron, yeah, sure, this electron, when it leaves, it's going to leave a hole. And when it does, that hole is going to neutralize this high-pressure part, because this high-pressure part is just a dense amount of stuff. So this is going to be neutralized by this electron flying out and around the nucleus. But this low-pressure part of the wave, this long drawn-out low-pressure part of the wave, which is good for accelerating loose stuff, but not something that's in a hole like this, this low-pressure part of the wave will, when it travels on and eventually hits an electron which is stuck, that is firmly stuck, like for example one of these electrons, or electron somewhere else in an atom adjacent to it or nearby, when this low pressure area hits an electron which is connected to the nucleus, what that's going to do is it's going to, say it hits this electron here. When this electron is hit by this low pressure part of the wave, maybe from another wave that got neutralized, it will accelerate into that low pressure. So here's your long low pressure zone here, and now it's being accelerated into it. Why? Because a low pressure is just a bit of a hole for it. So it accelerates towards it. But it's not going to come out of its hole here. It's just going to accelerate towards it, thus pulling the whole atom towards it, which is why this atom of iron in this matrix with the other atoms around it is able to accelerate towards the wave, the electron wave that was being made. So the magnet that's over here somewhere that's making waves, it moves the iron towards the magnet simply because it's producing both high and low pressure. So here you got a magnet over here, right? And this magnet over here is producing both high and low pressure waves because it's moving electrons. Now magnet, if you have like a north and south pole, like north and south pole to this magnet here, what you're really doing here is the electrons here are moving around in circles like this way, and so this way, and so that's producing waves because it's moving electrons in an ocean of matter, and those waves are you know, the high and the low pressure part of the waves are streaming off. The high pressure part is absorbed by throwing this electron around in this shell, but the low pressure part is not satisfied, and when it hits another electron, yeah, this low pressure part is not satisfied, so when it hits another electron, it accelerates that electron back. But because this electron's stuck in the iron, it pulls the iron back it pulls the whole iron atom back that way towards the magnet for the ride. So this is why, because of low pressures in this ocean of matter that we're all in, this is why iron is literally sucked back towards a magnet. It's not magic, it's not matter acting at a distance, it's simple physics. But now the electron in the iron, one electron per atom in the iron, once it's hit by the waves, is now moving around the nucleus, inside the nucleus, and outside all the other, you know, it's moving outside the nucleus, outside all the other electrons that surround the nucleus, and inside that one electron that's bonding between atoms. So it's moving around like this, you know, one electron per atom, and now that it's moving, it is now a magnet too, because it's now producing the wave as well. And so you can actually conduct that magnetic effect through a large amount of iron objects, depending on how great the waves are. Because if you can get the iron to get very efficient arrangements and faster, you can get the electrons to keep going for a long time. And that's how we make permanent magnets. They're permanent, but they're not really permanent. The electrons still run down over time as they're producing the waves. Some will run down faster, some will run down, it'll take years for some to run down, because you can make very efficient arrangements with even with just straight iron. But you know, you add other things to it. You know, you have neodymium magnets, last a really long time, really strong, still run down over time, still need replaced. Like, for example, if you're using them in generators and things like that, you still need to replace the magnets. You know, get the nice, best, strongest magnets, you know, for your generators or other applications. Here we have a magnet with a nail stuck to it, and it's an iron nail, a nice soft iron nail. Now we can actually conduct the waves through the iron to this other nail, and this other nail will dangle there. Now, if I disconnect this iron from here, the other nail will drop to the floor. It took a little bit. So we can see that iron really does conduct magnetic waves through it. So that's the magnetic effect. But how does diamagnetism happen? Why do some things get repelled by a magnet? Diamagnetism has to do with conductivity. If you have a conductor and the incoming wave is traveling this way, then the electrons in the conductor will travel towards the incoming wave because they're loose. They're loose in a piece of copper like this. Or if this was silver, or if this was just any conductor, gold, if the wave's coming this way, then... So here you have a copper pipe, and here you have a magnet. And when we drop the magnet down the copper pipe like that, you can hear it. It's coming, it's coming, it's coming, but it's taking a long time. There it is. And the reason it took so long was because the magnet had to travel down the length of the pipe all the time while it's shooting the electrons the opposite way that the electrons are traveling in the magnet. Now the reason why that happens is the magnet, okay, we're going to look at the end of this magnet. The magnet here has the electrons, now it's pointing right at us, so we're looking at the North Pole. The electrons in the atoms, they're all going this way, which would be clockwise. So they all produce an overall wave that shoots clockwise, like this. When it's dropping down the hole here in the copper, everything's going counterclockwise. Now that's when the electrons are flowing in the copper, that satisfies the low pressure. That satisfies the low pressure part of the wave, but the high pressure part of the wave is not satisfied. So the high pressure part of the wave travels on and slams into the electrons in the magnet and in the copper. And so it acts like the copper and the magnet are repelling each other, which is why it takes so long for the magnet to travel down the length of the pipe. Some materials are consistently diamagnetic, and some are non-consistently diamagnetic. If you have a superconductor and the electron arrangement in it efficiently allows the electrons to flow easily, like in a superconductor or like in bismuth, you can have a material that can float a magnet above its surface. With bismuth, bismuth is constantly diamagnetic because it's consistently, you can float a magnet over bismuth. If this was bismuth plate, you could float a magnet over bismuth constantly if the magnet was strong enough and the bismuth is thick enough, and you might need a lifter magnet, but you can stabilize it right between bismuth because bismuth is constantly diamagnetic, whereas copper, aluminum, gold, silver is not consistently diamagnetic. You have to run into new bismuth with a magnet, you have to run into new copper or new silver with a magnet and keep going across the silver or with a magnet in order to experience the diamagnetism, or you have to pulse it with a magnetic pulse. It has to be a changing magnetic field for conductors to demonstrate their diamagnetism, and that's because the electrons are loose, but they're not that loose. With a superconductor, they're very, very loose, and you don't have to run into new material with a superconductor. You can just float the magnet above the superconductor. The same thing with bismuth. You can just float a magnet above bismuth, and it's consistently diamagnetic. But it's diamagnetic because, unlike the superconductor, the electrons are not flowing between atoms in bismuth. The electrons are flowing inside, that is circulating inside each individual atom. Again, a lot like the iron. The affected electron is not jumping between atoms in the bismuth. The affected electron is encased inside just one atom, and that's why the efficiency is so great, and that's why bismuth can be, and pyrolytic graphite, for example, can be very diamagnetic without being a superconductor. And that's basically it for diamagnetism. This same thing is happening with the electron, where you have an electron here. Let's take a look at, say, bismuth. Here you have the nucleus. Here you have the electrons on the outside. And here you have the affected electron that ends up rolling around. When the incoming wave hits the electron in this, say, bismuth,
in this bismuth atom, what happens is you've got the high pressure part here, which when it strikes this electron here, it bumps it back a little, but then it doesn't affect it enough. What happens is this long drawn out low pressure area affects it much more, because this electron, although stuck a little bit in a hole, is mostly loose. And that's the key. Unlike the iron that's stuck in a tight-fitting hole and will ignore this low pressure because it's not strong enough, this electron will mostly ignore this strong pressure here because it's not long enough. So this long drawn out area here, because this is a wave, and this wave, when it's traveling this way, this electron, when it contacts this low pressure area here, it's drawn backwards into the low pressure and is accelerated this way around its atom like this. So you've got the low pressure area. So this bismuth is the opposite of the iron. Remember the iron? See, there's the bismuth with the affected electron traveling towards the wave. Here's the iron with the affected electron traveling away from the wave. And this electron here neutralizes, by falling into the hole, the low pressure part, but the high pressure part is not satisfied, and because this high pressure part is not satisfied, it travels on, slapping into another electron and bumps that electron back away. So that bumps the whole atom back away, which bumps the whole piece of bismuth back away. And that's why bismuth is repelled by a magnet. It's simply because the affected electron satisfies the one condition, that is the low pressure, instead of the high pressure part. And the high pressure part that's not satisfied is satisfied by bumping the whole atom back away from the magnet, which is why things are diamagnetic. Again, it's not magic, it's not forces acting at a distance. There's no such thing as a force or a property to matter. Matter just simply exists. That's all matter does. That's all matter ever did. It's just simply there. Just marbles to be played with. Just simple physical interactions of one item bumping another item. And that's all. That's all it is. It's all just a game of pressure. Simple physics. No actions at a distance. And that's diamagnetism.
So what have we learned today? We've learned that magnetism, that is magnetic fields, don't actually exist. It's simply waves traveling outwards, affecting different matter that's stuck in different ways, differently. That's why some things are repelled by the field of a magnet, and that's why some things are repelled and some things are attracted to a magnet. It all is determined by what situation the stuff is, what arrangements the stuff is in, and that's what determines what happens to it. Like a child playing in a sandbox, or a small or big game of marbles, just playing with marbles, that's all this ocean of matter is. It's just simple physical interactions, and once you know what's going on, it's not that the wonder is gone, it's that it's amazing what you can do with just marbles. And that's all of this stuff really is. It's just a large game of marbles.